Here we have another example. So an Airbus jetliner has takeoff mass, so we know M, reaches a takeoff speed of 82 meters per second in 35 seconds. So let's see, let's say we have our plane. I'm assuming it's starting at rest, waiting to taxi, so it's waiting at the end of the runway. This problem tells us it reaches this takeoff speed of 82 meters per second in a time of 35 seconds. Since that's the takeoff speed, I'm assuming the plane is on the ground, on the runway, this whole time. We want to know the thrust of the engines. We can neglect drag, but not rolling friction. They tell us the coefficient of rolling friction between rubber and concrete is 0.02. All right, so free body diagram. We imagine this airliner sitting, well, it's on the runway, it's not sitting. As it moves from this initial to final point, it's moving. We do know there's the force of gravity. It's being attracted to the center of the earth. Because the plane is still on the runway, there's going to be a normal force from the runway pushing up. The problem mentions rolling friction, so we do need to account for that. That rolling friction opposing the motion. And then the problem is asking for the thrust of the engines, that forward thrust that's causing the plane to speed up. All right. Since the plane has not yet taken off, that thrust still is directly forward, so we're not lifting off the ground yet. Now that we have the free body diagram, we've accounted for all the forces. We need to write out the net force equals ma for the x direction and the y direction. Now, in this case, the plane is speeding up. It takes 35 seconds to get up to its takeoff speed. So we do know there's an acceleration in the x direction. According to my picture, that's to the right. So when we write out the net force in the x direction, we're going to have the force of thrust to the right. We'll have friction, rolling friction, to the left. So that is the net force in the x direction. This net force, this combination of forces in the x direction, is determining the acceleration in the x direction. So net force equals ma for the x direction. In the y direction, we have the normal force upwards, force of gravity downwards. Those are the only forces in the y direction, so that would equal mass times acceleration, but for the y direction specifically. Now again, because it tells us that it's reaching the takeoff speed at the end, we're assuming it's not lifting at all off the runway, and so that acceleration in the y direction would need to be 0. That leaves us with the normal force needing to equal the force of gravity in this case. All right, so these are the symbolic equations. Every problem on your test, which I highly recommend as you're working on your homework, is going to require a free body diagram and symbolic equations. So I'm going through the process of doing those all first to help you learn the process. All right, so going back to the problem, ultimately what we want to find is the force of thrust. That's what's being asked for. So if I plug in here, force of thrust, we know the force of rolling friction would be the coefficient times the normal force. That net force has to equal ma. So the force of thrust is going to be mass times acceleration plus mu, which we are given. The normal force from the y direction, I know needs to equal mg. So I'm going to go ahead and plug that in as well. So we know the mass of the plane, we know g, we know mu. We want thrust, but we don't have acceleration yet. We've already written the equations in the x and y directions, and the acceleration only shows up in the x equation. So we need some other sort of equation that could allow us to solve for acceleration. And that information is going to come from this motion. So similar to the previous section, if we had been told, hey, you have a plane at rest, it's going to reach a velocity of 82 meters per second in 35 seconds, what is the acceleration? That is something we could have totally solved for, even in the last section. So the plane is starting at rest. We know the final speed and the time it takes to reach that final speed. So we can solve for acceleration here. Knowing the acceleration, we now can come back to our force equation and plug these values in. Since there's a mass in both terms, just for simplicity of plugging values in, I'm going to factor out the mass. We know the acceleration. We know the coefficient of friction. And then g, of course. So plugging these values in, I'm getting a really big number. And by the way, we don't like counting decimal places if we don't have to. So let's write this in scientific notation. So 1.9, 1, 2, 3, 4, 5 times 10 to the 5th. This is a force, so the units will be newtons. But just to prove that to yourself, the mass we have here is kilograms. Acceleration, meters per second squared. And that's true for the second term as well. G has units of meters per second squared. A kilogram times meter per second squared is a newton. So we do have the appropriate units for force. This one, we do have an acceleration. We see it speeds up in some period of time, which is why we can use the kinematic equations.